Hello everyone, welcome back to this week's algebraic graph theory seminar. This week, Vincent Schmeits, he's going to talk about periodicity in vertex-face walks and roots of unity.
Okay, thank you, Tina, and also thank you for organizing this seminar and for giving me the opportunity to talk here. So today I'm going to talk about some work that's already been done quite a while ago with together with my supervisor Krystal. So some of you may have seen this talk or parts of this talk before, but at the end I've put some new stuff about some new, or like let's say more recent work that I haven't talked about before. So maybe that's nice for people that have seen stuff about this before already. So let me get started. First, I'll say a little bit about discrete-time quantum walks in general, because this vertex-face walk that I'm going to talk about is some type of discrete-time quantum walk. Then I'm going to give the definition of the vertex-face walk itself, and give also definitions of perfect state transfer and periodicity in this walk specifically. And related to these two notions, we'll see that some Chebyshev recurrence comes up in a sequence of certain matrices that are obtained from projecting down the walk in some way, but you'll see it later, how that works exactly. And then at the end, I'll say something about perfect state transfer and periodicity in toroidal grids, which are just certain embeddings of grids on the torus. And the new part will be that I actually show some tricks that we use to actually give the classification of all grids that have PST and periodicity, which I think have some cute kind of tricks that are not too complicated. So I thought it was nice to show. So the setting is quite simple. I won't really say anything about physics, and you guys in the seminar are probably familiar with this kind of topic. So yeah, it's not too complicated. I'll just call any state is just a vector of length 1 in the like in a complex vector space like this, and then of course if we have a vector in this space of length 1, we can write it as a linear combination of these standard basis vectors, and we say that these standard basis vectors are kind of the classical states in the space, and every other state of length 1 is a superposition over these classical states. And if you look at all these coefficients, if you square them and you add them up, you get 1. So this gives you a probability distribution. And always the quantum stuff is kind of like you do a measurement and you find, if you measure this state Z, you find one of these classical states with the corresponding probability. So that's kind of the linear algebra setting here. And now if we have a unitary matrix and we multiply it with a state, because a unitary matrix retains the lengths, we get again a state, namely a vector of length 1. So we can keep multiplying some initial vertex or initial state with a specific matrix U, a unitary matrix, and we get a sequence of vectors that we call discrete-time quantum walk. And there's also a continuous version of this where it's like a U is kind of a continuous function in some way, continuous matrix, depending on some T, I guess. But now the times are discrete, and these will just be the powers of U, and we will call U the transition matrix of the walk. All right, so not really new stuff, probably. So let's dive slightly deeper. Simple examples of unitary operations are, of course, reflections and permutations, but these are maybe too simple to really, there's not much to analyze for this kind of operation, I guess, in a quantum walk. But like maybe the most simple, less trivial operation would be a product of two reflections like this. And then the vertex-face walk that we're going to define also has this form. And here P and Q are orthogonal projections, which makes these expressions actually reflections. Like they're symmetric and they're involutions. And you could say that, for example, this reflection 2Q minus identity is a reflection in the column space of this matrix Q, which means that if you have a vertex or a vector in the column space itself, then this reflection does nothing to it. If you have a vector orthogonal to the column space, So in a kernel, then you go to the negative vector. So that's how it acts on these vectors, and then you say that it reflects in the column space. So what we'll do for the vertex face walk is we'll define two of these reflections based on an embedded graph. And how that works is like this. So we have initially, let's start with a planar graph embedding. So this is K4 embedded in the plane. And it has vertices and edges, but also faces, because we have an embedding. And the faces are these disjoint regions that are now disjoint because we have an embedding. What we do, so the walk will actually take place on the space indexed by the arcs and not the vertices itself. And these arcs, we obtain them by replacing every edge by two arcs going in opposite directions. And because we have this nice planar embedding, we can do it in such a way that every arc, if we look at each face and we look at the arc that's kind of incident to this face, or like lying inside this face, we'll see that the arcs go in a clockwise direction. And this is true for every face here. Also for the face on the outside, because actually we're looking at, you can see it as an embedding on the sphere. So for the outside, you need to look at it from the other direction, kind of, and then it's still clockwise and not anti-clockwise as it may look like. So I write it here. You have to do it in such a way that they agree with the clockwise facial walks. So it's a bit elaborate, but now we'll use this kind of, what we have done now is we've made kind of incidences between arcs and faces, and we also have incidences between arc and vertices. And as I said, the state space will be indexed by the set of arcs. So this space corresponding to this embedding will have dimension 12, for example. All right. And then what we'll do for the first reflection, we'll take, for example, we'll denote, like, if we have an arc, maybe this arc on the bottom. I hope you can see my mouse, by the way. Then the arc on the tail end of that the vertex on the tail end of that arc will be denoted by V of A, and this will be the vertex that is incident to this arc. So this vertex is not incident to this arc because it's the head, but it's the tail. That's what it's about. It's kind of, the choice is arbitrary, but it doesn't really matter. But this is what we'll do. And then for every vertex, we'll define this kind of vertex state. That's a uniform superposition of all the arcs that are incident to that vertex. So I sum all these standard basis vectors or classical states, if you will, and I normalize them, and then I get this length 1 vector that's this kind of uniform superposition. And I do this for every vertex. I make one like this. And then I've kind of partitioned all the arcs corresponding to the vertices in some way. And then the projection Q for the reflection will be the projection that projects onto the span of all these kind of vertex states. And in an image or in a picture, so this is a bit vague, this statement here, but if you would start in a standard basis vector, then this reflection would reflect it in this one-dimensional space. In a picture that looks like this, so I have my initial vector here. You can see this is the standard basis vector. If I apply this reflection once, I do kind of a redistribution over all the arcs that come out of that same vertex as the initial arc did. And here the colors are like positive and negative. So blue is negative, red is positive, as you can kind of see here. I now have this updated vector, and this is what the first reflection does. And note that this reflection does not depend on the embedding, it's just vertices and arcs. But the second reflection, there will be kind of the dual notion that will depend on the embedding, because now we care about faces instead of vertices. And now we have a similar thing where we look at an arc and we look at the face inside which the arc lies, or maybe along which the arc lies, as I've written it here. And then we define kind of a face state like this. That's all the arcs incident to that face, similar as we had before. And then similarly, P is now the orthogonal projection onto the space spanned by all of these states, like the subspace. And we have a similar picture, but this time what the reflection does is, if I start in a classical state like this, and I apply the reflection, it does the redistribution in this way. And it is actually the dual thing here, because if you would look in the dual planar graph, then and you would connect the correct arcs to the correct vertices, then this would actually be kind of the vertex reflection in some way. So it is actually, these are dual reflections in some way. Let me get some water. And if we take the product of these two reflections, then we get something called the vertex-face walk. And this was defined by Harmony Zhan in around 2021. Yeah, I've just made a picture to kind of show some evolution of the walk. Maybe it's not very insightful, but if this is your initial state and you would apply this U multiple times, then after one time step, you would kind of get this state, which with the values here on the right for the entries. And you can see there's no arc on some of the edges. There's an arc missing, and that means it's still 0 there. That's for these entries. That's at time 1, so you've not really reached all the arcs yet, but at some point it kind of diffuses, and then I've just put some steps here, where also the opaqueness in the color gives the amount of kind of amplitude that there is on the arcs. But yeah, so that's a small animation basically. So until now we've defined it for planar embeddings, but you can make this a bit more general. So we can go to orientable maps, which are 2-cell embeddings of graphs onto orientable surfaces, where in this case an orientable surface is just like a sphere with some number of handles attached to it, or with some number of holes in it, like in the torus or double torus, and that's the genus of the surface. And then it's like, I think, compact and closed or something, or bounded. I always forget the correct assumptions, but that's like all the orientable surfaces. And then a 2-cell embedding means that every face of the embedding, so the disjoint regions that you make by embedding the graph onto it, every face should be homeomorphic to an open disk. So this is another example of K4, but this time it's embedded in the torus, where the top and bottom here are identified, and left and right are also identified. So we've got these 4 edges here, and then there's 2 remaining edges going kind of around the torus, around the handle, basically. And now we play the same game, so we replace every edge by 2 arcs, and because it's orientable, we can still do this nicely in such a way that all the faces are oriented clockwise. And this time for the K4, we have a face of size 4 in the middle, and then here on the outside, we have a face of size 8. So with kind of 8 arcs going around it. And you can actually make it even more general. You can do non-orientable surfaces. You probably don't even need like 2-cell embedding, but now you lose some duality, I guess. But yeah, you just keep losing more structure. So maybe let's keep it like this. This was enough for the things we looked at in our paper. So yeah. So next up is the definition in the vertex-face walk for perfect state transfer. That is, if you have 2 vertices that are distinct, and you start in one of these vertex states. So again, it's kind of uniform superposition of all the arcs coming out of one vertex. And then after applying this U a number of times, you arrive in the same, or like in another vertex state, phi of V. So the same state that we had before. If this happens, then we say that there's perfect state transfer, and the time of perfect state transfer is tau. And we will sometimes write UV BST to keep it a bit shorter. And if they are the same vertex, then it's actually periodic. There's periodicity at U at time tau. So maybe we won't stay in U, but at some time we return in U, then it's periodic. And now I have kind of a trivial example of this, which is this. You have 2 vertices with a number of edges going between them. And I've already replaced all the edges with 2 arcs, and I've already colored in the first, or the initial state, which is the vertex state around this vertex. So for this one, you'll see that after one time step, you're already in the other state. So there's perfect state transfer from this vertex to this vertex at time 1. And by symmetry, at the next time step, I will be back in this first vertex. So it's also periodic at time 2. And note that this is also an embedding, right? So the faces here are kind of these size 2 faces here in the middle and on the outside. So it is really about the embedding. Yeah. All right, but so this example is a bit trivial maybe, but it turns out that it's actually quite hard to come up with other examples of perfect state transfer. And this is also perfect state transfer at time 1. And you can ask maybe, is there perfect state transfer at any time? Is there periodicity at any time? So to get a bit of a better handle on this, we needed some more tools. So for that, I'm going to define some more matrices. So now I'll define this matrix N to be to have all the columns to be these vertex states that we defined before, all these uniform superpositions over the vertices. Every column of N is one of these states, and N itself is indexed by the arcs and vertices. Now, because all these states are orthogonal to each other and they're also length 1, that means they're orthonormal, and also the space that Q now projects onto is exactly the space spanned by all of these states, which means that the column space of N is exactly the column space of Q. That means that Q can actually be written in this way. I've written a star, but I could have written a transpose because it's all real, but I'll take a step back later to a more general setting. So I just wanted to keep stars like Hermitian transpose for all my matrices, just to keep it safe. With this definition of N, we can rewrite some stuff. So if I now have perfect state transfer from U to V, so I start in this state, after tau time steps, I'm in this other state at V. Then if I multiply both sides by phi of V star from the left, I get a 1 on the left because it has length 1, and I get this number on the right. And if I now plug in this matrix here, I get this expression, where you actually have this smaller matrix in the middle. And the smaller matrix is now vertices by vertices. And this means actually that you're looking at the VU entry of this smaller matrix. The smaller matrix we will call B of t or B sub t, because for every power of U we have a different PT. Okay. And then this would be like the VU entry of that matrix BT, basically. And then we have a lemma that says if you have two distinct vertices, then there's UV PST at time tau, if and only if actually that entry is 1. So one direction we've already seen. So if there's PST, then we know that that entry is 1. The other direction follows from a simple geometric argument. So we have kind of another characterization of PST here. And there's also periodicity at U at time tau if, I mean, that's kind of the same statement, but now for the diagonal element, if that diagonal element is a 1. And let me see. So we can already use this to say some stuff. So note that I've given the expression here for PST, like the equivalent characterization. We'll see that this BT is actually symmetric because what can I do? I can expand all these powers, or I can expand all these U's in this kind of alternating product of these two reflections. And then you'll see that at the end, you already saw that we wrote this Q as N transposed. I mean, this reflection will do nothing with the column space of N because it's actually the column space of Q. So all I'm saying is that this reflection, we can disregard it and it just disappears. And now we get kind of this symmetric product where at the start we have the same reflection as at the end. And if we would take the transpose of this, we would get the same thing actually, because these matrices are all symmetric in the middle. Which means that if I have UV PST, then the VU entry is 1, but also the UV entry is 1. So there's also VU PST at time tau. So we have kind of this monogamous relation. And also, of course, now I go from u to v with time tau, but also from v to u with time tau. So I come back in u at time 2 tau, and the same holds for v. So there's also periodicity. So if there's PST with this definition, then there's also must be periodicity like that. And then I have one more definition that will come back later a little bit. And this is because those embeddings of toroidal grids that will come in the next part of this talk, they're very symmetric, and they will have the property that if there's periodicity at one vertex, then there's periodicity at every vertex. And you would then say that there's periodicity everywhere, and that the map is periodic. And so what it says here is that actually u to the power tau acts as the identity on the space spanned by all these vertex states. And we have a theorem here that says if that's the case, then actually almost any time that happens, u to the power tau itself is the identity. So that's actually a stronger statement a priori than just on this subspace kind of. And the required conditions are like one of these needs to hold. So if tau is even, then this is definitely equivalent. So I've written periodicity everywhere. That's this thing for all u. But it also happens if the number of vertices is equal to the number of faces. Then this is also equivalent. And of course, if there's periodicity everywhere, then definitely at time 2 tau this equation holds because 2 tau is even. So then you're in this case. So that's definitely true. And as I said, we'll need this later. So yeah, keep that in the back of your mind for now. And let me take a step back now, where I'll look at a more general kind of two reflection unitary matrix. And still we'll define again this kind of B matrix, but I've used some different letters to make clear that this is like more general than just for the vertex-face walk. So now I have reflections with X and Y as the projectors. And we write Y as kind of this this product with some W, and we project kind of this U to the power T down onto the column space of W in some sense. That's what this does. So this B is again a smaller matrix. It's the same thing as we had before, but in a more general setting. And now we have this nice theorem that says that BT, it's not like B1 to the power T or something, but it is a polynomial in B1, and namely the following polynomial. It's the Tth Chebyshev polynomial of the first kind. And then initially you wouldn't be able to maybe guess. I mean, you could guess that it's true, but you're not sure. And this actually proves that BT is a polynomial in B1 for every T. To give a bit more insight on this, so these Chebyshev polynomials are defined by the following definition. If you would have a cosine here, you can kind of, the polynomial of that cosine would be the cosine of where you put t inside the cosine. Basically, there's also a recursive definition that's equivalent to this. And it says that like the 0th Chebyshev polynomial is 1, the first Chebyshev polynomial is x, and then you have this two-step recursion for all the other Chebyshev polynomials. So both of these uniquely define the polynomials that give this recurrence, basically. And then, of course, you can also write it in terms of matrices. Specifically, the B0 would be the identity, B1 would just be B1, and then we have this two-step recurrence for the sequence of B matrices, which again can be used to analyze some, I'll show it on the next slide. This BT matrix can be used to give a necessary condition for perfect state transfer, and a better one than we had before. So we already had that this entry corresponding to U and V needs to be 1, but now we'll say something more. Namely the following: if there is U VSP at any time, or at some time, I guess, then U and V must be strongly cospectral with respect to this matrix B1. And you might have seen it before, but let me just give the definition again in that case. So Zorny cospectral means that if I write a spectral decomposition of my B1, where the thetas here are the eigenvalues and the E's here are the spectral idempotents, then for all these spectral idempotents, I need this condition to be true. So the youth column of each spectral idempotent needs to be plus or minus the vth column of the spectral idempotent. Let me see what time it is. Okay. I had a proof of, so this is the definition of Zorny cospectral. I had a proof of this corollary, but maybe I won't go over it. It's relatively simple, but in the interest of time, I should continue, I guess. But just to summarize, this gives you a necessary necessary condition for PSD to occur, and it's quite a strong condition, I would say. And the nice thing is that you just need to look at this B1 and not any further time. Just if you know the spectral decomposition of B1, you have a nice handle on that decomposition, then you can verify this and rule out PSD from happening, possibly. And now I want to give examples. For the remainder of the talk, I want to focus on toroidal grids, which I'm going to define now. And I'm going to characterize periodicity and perfect state transfer in these toroidal grids. So what is a toroidal grid? It's just an embedding of this Kronecker product of two cycles, Cn and Cm in this case. And the embedding will be the following. I just have the cycles of length m going horizontally and the cycles of length n going vertically. And this is kind of that box product. As you can see, you get all these kind of boxes. So these cycles wrap around the torus like this. And actually, we'll also allow multigraph. So maybe they're not cycles anymore if you don't like that. But if the minimum of n and m is like at most 2, then you can get kind of multi-edges here, like one edge going this way between two vertices, one edge going the other way between two vertices. We even allow loops. So in this case, you would maybe have a big cycle around and then a bunch of loops going around the torus. And actually, these will give examples of perfect state transfer, as I will show next. But first, let me give another like small animation because we like pictures. So if we would start in this initial state, again, it's a kind of vertex state corresponding to this middle vertex here. Then in the vertex face walk, in the next step, I've kind of diffused a little bit more to all the incident faces, and now I'm also incident to new vertices. So I keep kind of, this pattern keeps growing until I've filled the whole torus. And this diffusion kind of, it's completely diffused now, and it's kind of a random pattern. And I can tell you that there will be no PST or perfect or periodicity happening here. At least in the first like 15 steps, you see that it doesn't happen, so that's good. But now some cases where it does happen. The first case is the following. It's this kind of the grid that I talked about before. It's you have a big cycle of length m, and then you have all these loops going around. So n is 1. Or maybe it's the other way around, right? You could also have n, the m,1 grid, but we'll just say it like this. This grid is always periodic at time m. And if m is even, then at half the time of that period, there will be perfect state transfer to kind of the antipodal vertex. I'll show this later in a picture as well on the next slide. And there's also the one with 2 rows. So you have 2 cycles with kind of these digons connecting them at m places, basically. If this time, if m is even, then it's periodic at time m. If m is odd, then there's perfect state transfer at time m, and the map is periodic at double the time. So these are 2 cases where you have perfect state transfer and periodicity. And to give you a small insight into why this is true, let me define the following matrix. So capital Pi is the cyclic permutation matrix that sends a standard basis vector EI to the previous one, and this kind of cyclic, so it's modulo m in the index. So it's just this permutation matrix. Then using this Chebyshev recurrence, it's possible to prove that actually the BT matrix for the 1M grid has this form. And you can already see, so if I would take T equal to M, then this becomes the identity matrix because it's a periodic matrix. This also becomes the identity matrix. So the whole matrix here becomes the identity. And then I have ones on the diagonal, which means that there's periodicity at every vertex at time M. Because that was the kind of what we could use this matrix for. And then as a side note, if M is even and L is half of M, then BL will be this matrix because now BL is equal to, or like pi to the power L is equal to pi to the power minus L. So you get this thing, and then you have kind of this involution that also tells you which are the vertices that have PSD. You get like a matrix of zeros and ones, but not on the diagonal. Okay, anyway, and then for the 2M grid, the expression is a bit more complicated. Of course, this depends on how you've ordered your vertices. That's also in this case. So I've ordered it in such a way that you can write it nicely like this. But you can already see here that if M were to be even, it's kind of a sum of this Kronecker product with this Kronecker product. If M were to be even, you get 2 times the identity here. You get minus 2 times the identity here. So this term disappears. And then you're left here with the identity. So again, there will be periodicity at time M if M is even. Okay. And here I have some pictures. So this is what it looks like. If my initial state is this, then you will kind of see the state walk around to the other side. So we get at half the time of M, which is at 10 in this case. So that's at time 5. You will arrive at this antipodal vertex, which is exactly on the other side of the torus. And then in 5 more steps, you're back where you started. So note also that it doesn't really diffuse this time. So stuff really cancels out so that you get a lot of 0 arcs and it just kind of walks to the other side. And a similar picture for the 2M grid, where this time I've taken M to be odd, namely 7. And I said if M is odd, then you have this perfect state transfer. So what happens here now is you start at this vertex here. Then after 7 time steps, so M, I'm in the vertex below. And after 7 more steps, I'm at where I started again. So that's periodicity at time 14, PST at time 7. Okay. And then for the remainder of this talk, that's kind of the new part, I guess. I'm going to prove that these are actually the only cases of PST and periodicity, aside from one more sporadic case where it's the 4x4 grid. This one will have periodicity. Of course, I have another picture. No PST this time, but it will kind of diffuse, and suddenly at time 12, you'll see that you'll get back into this first vertex. So this one has periodicity. The 1-row grids and 2-row grids have periodicity, but all the other grids have no periodicity. And I'll give an idea of how to prove this now, which I thought has some kind of nice, simple tricks. And for that, I'll go back to this theorem. So for the grid, if there's periodicity somewhere, there's periodicity everywhere. So that means, I mean, the number of vertices is equal to the number of faces. So always we'll have, if it happens at some time tau, then definitely u to the power tau needs to be this identity matrix. But that's very restrictive, right? Because what does this mean? It means that the eigenvalues of u are all roots of unity, tauth roots of unity to be specific. So what happens then? The characteristic polynomial of u must factor into cyclotomic polynomials over q. That's necessary. And these cyclotomic polynomials, they're exactly the irreducible factors of these polynomials of this form over q. And they'll always have like the roots of unity as their roots. And in particular, these cyclotomic polynomials have integer coefficients. which means that since u now factors into these cyclotomic polynomials, if this is true, so if there's periodicity, then all the coefficients of u of this characteristic polynomial of u must be integer. So quite a simple test would be like, if I find a coefficient of my characteristic polynomial that's not integer, then I know immediately that it's not, that there cannot be any periodicity. And I think in this case, for the grids, the coefficients are always rational. Or maybe that's not true actually, but they're definitely not always integer. And then with that, you can rule out a periodicity from happening. So let's just look at some coefficients then. For that purpose, I've written the characteristic polynomial in two different ways. This is just, I have all the powers of x in my polynomial and then all the coefficients, the ci's. But I can also write my polynomial as a kind of, I've decomposed it into all the linear polynomials with the eigenvalues here. So these are roots of the polynomial, of course. So the lambda j are the eigenvalues of u. And then, well, of course, this first coefficient is 1, because if I would expand this, I would get all the x's, and I would get just 1 everywhere. So this is my first coefficient. And then the second coefficient, actually, I will take again all the coefficients for these x's, like they're all 1. I'll take 1 lambda j for every j. And then if you would do this expansion, you would see that the second coefficient is equal to this number. So it is the sum of all eigenvalues, and then negative that, which is actually minus the trace of u. So if this number is not rational, or is not integer, then there would be no periodicity, right? However, sadly enough, the trace of u is actually n times m. This is always integer, so no luck. But we can go one coefficient further, and that's this expression. I just take all the pairs of distinct, maybe I shouldn't say distinct, but I take all the pairs of ordered eigenvalues like this. Yeah, and also in an ordered way. I can rewrite this in the following way. Instead, I can take the sum not just of these ordered pairs, but of just all the pairs. But then I've collected too many eigenvalues, so I need to subtract those pairs where j and k are equal. But also they're not ordered anymore, so I need to take half of that, and then these two expressions are equal. And now if you look closely, this is actually this expression. So I get the squares of the eigenvalues here, which will in the end lead me to get the trace of u squared. And this will be equal to the trace of u, that whole thing squared, the whole trace. And then I still need to divide by 2. So I have this expression. And the nice thing, again, I think you can continue this for more coefficients, but the nice thing is that it's not in terms of the eigenvalues, but just in terms of the trace of u and u squared. So I've given the expression here again. So this number is always integer. But what do we have now? This other number, trace of u squared, that's not always integer. It's actually, you can show that it's equal to this number with some simple computations, if n and m are at least 3. And then if I plug those values in this expression, I find this. Where inside the brackets here, I have an odd value, because this is always even, this is odd, so the difference is odd. And then I have this 1/8 times nm in front of it. And because this is odd, this means that this coefficient is, it's integer if and only if n times m is divisible by 8. So proposition, it's periodic only if n times m is divisible by 8. Only then can it be periodic. So this rules out already a lot of those remaining grids, right? If n times m is not divisible by 8, then surely there's no periodicity. So that's already some part of the way. Yeah, forgive me for this last part being a bit technical, I guess, although it's not too complicated, I would say. But yeah, we have some remaining cases left, though, those cases where it's not divisible by 8. So let's try to look at that. And for this, we'll go back to this B matrix again. which is now denoted by B, just to simplify the notation a little bit. Again, if u to the power tau equals I mean, then of course this B matrix also needs to be I at that time tau. So the B of tau needs to be the identity. And we had this expression in terms of the original B, where we take this Chebyshev polynomial. Looking at the spectral decomposition, you can then argue that, okay, then actually if I plug in this eigenvalue of B, then at time tau, or like the tau Chebyshev polynomial, for that value lambda, it needs to be equal to 1, because that's kind of the eigenvalue of this B tau here. So that's a requirement for this PST to happen, at least, or periodicity, I should say. And we do have expressions for these eigenvalues, so it gets more ugly now. So the eigenvalues of B for this toroidal grid, they're given by this expression. These cosines, actually, you can get them from the adjacency matrix of the cycles. So the adjacency matrix of the cycle, the eigenvalues have something in terms of cosines that looks like this, that look like this, and then using that, you can prove that this is actually true for the grids. So we've just, all the eigenvalues are indexed by K and L. They may be, for different K and L, they may be equal, but this definitely gives you all the eigenvalues. Let me see, I don't have a lot of time left, maybe not 8 minutes or something. So we have another lemma, and that says that the NM grid is actually periodic at time tau, if and only if for all K and L, I can find some rational number that makes this equation hold, where this lambda K comma L is exactly this expression. And this has a small proof, because all these lambda K's and L's, they're like values between -1 and 1. You could kind of deduce it from this expression. So that means that I can write it as a cosine. So let theta K comma L be such a cosine, or like an angle that gives me this lambda out of the cosine. If there's periodicity at time tau, then B tau is the identity. So 1 is equal to this, as we saw on the previous slide, right, over here. This equation needs to hold. But now, because I've written this as a cosine, we have this property of the Chebyshev polynomial, where we just bring the tau into the cosine, and then it must be equal to this value. So now we have that cosine of this thing here needs to be equal to 1. So this should be an integer multiple of 2 times pi. Namely, I can let this be that integer. If I divide this by 2 pi, this must be an integer. And I can easily take my rational number like this. I can divide it by tau, and then clearly 2 times pi times q comma L is this theta. Which means that if I were to put it in here, I would exactly get this lambda K comma L because of this equation, right? And this is one direction of the proof. The other direction is, I think, not so difficult either. And this actually also, so the statement is not completely correct. I see it should just be, the tau should be gone. It should just be periodic if and only if blah, blah. And then you can get the time tau actually by looking at all these rational numbers and take the smallest tau that makes all of them integer by multiplication, kind of. So this tau should not be here actually in the statement. And now, as a small sanity check, you can use this to show that the 4x4 grid that we just saw, which had period 12, you can actually prove it with this easily. We need for all K and L with these values between these in this range to have this equation hold. Only then there can be periodicity. So there must be, we need to find these rational numbers, and then because the number, or like because we have n and m equal to 4, it's all quite simple, and we get really nice values for all these expressions on the right. And then that means it's also easy to find the corresponding rational numbers. So I've just given all the rational numbers. That means that there must be some time, and that time will be like the smallest number that I can multiply so that all these values are rational, or like are integer, the multiplication of that. So that would be 12 in this case. So this kind of table kind of proves that the 4x4 grid is actually periodic with period 12. And then the final stretch, it's maybe not very nice, but also kind of cool, I would say. There's this ancient result by Conway and Jones that says something about kind of sums of cosines with like rational multiples of pi as their arguments, and also kind of rational combinations of those things. And it's also stuff about roots of unity. But with kind of the result that this is based on theorem 7, that's about kind of cosines. And I've taken a small part of this. They're actually, this is just 2 cases, but there are actually way more cases. But still like a very finite list, so that you can just check to see when equations of cosines can hold. Because as you can see, we have an equation with cosines here, and you might say, well, does this even ever happen if my cosines are like this? Can I even, yeah, maybe this doesn't happen very often. So I've picked out 2 of the statements. I have some angles in kind of like the first quadrant. They are rational multiples of pi, and in that case, the following is true. The cosine of theta is rational if and only if theta itself is pi over 3, because I'm in the first quadrant. So that's nice. If I have 2 cosines that are kind of both irrational, but I have this, I don't know if this is the right way to phrase it, but I have this kind of linear combination of these, or like a rational combination maybe of these 2 irrational cosines. So this p and q, they're both rational, and their sum is rational, this sum is rational. If this is the case, then this whole combination must be like proportional to this. So what does that mean? Like p must be equal to q, but then the negative of that. And r must be half of p and q, something like that. And these theta and phi, they need to be like this multiples of pi over 5 in this way. And as I said, there are a bunch of more cases in the actual theorem, but this is all we need basically. And if you would extend maybe to pi over 2, then you get also some other values that this can take on. If it's, well, I mean, of course, the cosine of pi over 2 is like 0, so that's another like rational case, I guess. So yeah, maybe I shouldn't have put this first, but I'm going to use this in the final lemma. So the statement is as follows: I have this NM grid. If it's periodic and either n or m is divisible by 4, then we must be in a case where it's the 4x4 grid. And the idea is as follows for the proof. We assume without a lot of generality that n is the number that's divisible by 4 out of these 2. And then we take specific k and l, namely k is n over 4 and l is 1. And we only need to show that it fails for, let me see if that's the, if you would want to rule out periodicity, you would only need to show that it fails for 1 pair of k and l, because it needs to hold for all k and l. So we've picked some specific k and l, and in that case, this equation can be reduced to this equation. And now I have a sum of these 2 cosines, as you can see. And you can already see I have a 1 here as a coefficient, I have a 2 here. So I can never really have this if both cosines are irrational. And of course, I mean, I'm assuming that this needs to hold, so you need to kind of rewrite your equation to have them all in this first quadrant, all these angles, but those are some annoying details. So the second case here really doesn't happen actually. And you can use the other case, like the first case, to do some checking, and you can really verify that it can only happen if m equals 4, because otherwise this number is just too large, and if it's rational, then I mean, it cannot be rational anymore. So then you can already see that this condition fails. And now m is equal to 4. It takes some work to show that. But now m is also divisible by 4 because it's 4. So by symmetry, also n equals 4. I can do the same argument. I take k equals 1 and l equals m over 4. And I get that n needs to equal 4 as well. Okay, so maybe those were a bit too many details. but I still thought that there was some nice tricks. To summarize, what we've shown that the grid is periodic if you have kind of 1 or 2 rows, or maybe 1 or 2 columns. It's also periodic if I have a 4x4 grid. It's not periodic if n times m is not divisible by 8. That was kind of with the characteristic polynomial trick. If n times m is divisible by 8, then n or m must be divisible by 4, otherwise it never happens. And that's what the other lemma was for. Is not periodic if n or m is divisible by 4 either, unless it's the 4x4 grid. So this kind of covers all the cases. And with that, we've done the whole characterization, and we've actually proved the theorem that I had on a few slides back, that these are all the grids that have periodicity. Yeah, and that was it, I guess. So thank you for listening. Yeah.
Thank you. It's a very interesting talk.
Thanks.
So, any questions for Vincent?
I have a question.
Sure.
Yeah. So you're using the states that have uniform superposition on the arcs outgoing of a vertex.
Mm-hmm.
And I see that like well, the advantage of it is that B is symmetric. So
Yes.
I guess the analysis is easier. Can you push it so that you would have states that are kind of concentrated on the outgoing arcs of a vertex, but not necessarily uniform?
Yeah. So I've made it a bit more. How do you say? I've swept some parts under the rug. And indeed, what we did was we did not take the initial. We always take the initial state as this kind of uniform superposition, but then we did at first like allow it indeed to be only supported on those arcs, but maybe not uniformly, right? That's kind of what you. So we had this as an initial definition of PST. You do start at a uniform superposition, but maybe the superposition that you end in is not this uniform thing, but it's still like this kind of only on those outgoing arcs, but not specifically the same. If the degrees are the same of the initial vertex and the vertex where you end up, then this is actually equivalent to the definition that I gave. So then it can only be that this vertex that you end up with is the uniform superposition. So that's kind of a reason why we kind of restricted it to this case. Although if the vertices are not equal degree, this doesn't happen anymore. And you can also show that's in our paper as well, that it can only go from a vertex with, I think it's lower degree to a vertex with higher degree, and not the other way around. Or maybe it is the other way around, but it's like one way. With I guess the initial or like more general definition that you maybe gave.
So how much more complicated is the analysis if you lose the symmetry of that B matrix?
I don't really know, but now it's kind of the question would be maybe what would be the B matrix, because the B matrix really depends kind of almost on having this definition, I guess, because you get it by multiplying these kind of uniform states from left and right. I'm not sure if you, sorry?
Yeah, so instead of using the N where you have, I guess, like the same entries on right on the support, like if you kind of use different columns, and it's still like you have that WW star, right, with the W.
Yeah. So in that case, if your kind of starting states are these, or like you transform it kind of to another state space. So now they're not uniform anymore, but they're different. Indeed, you have these W's, and then the analysis is the same, I guess. Yeah. Then you have a kind of a new definition of PST, and it's really specific between these states, and it's but then there's maybe another position that's like coming out of these arcs, but it's like yet another distribution. So
Right.
then it's still, yeah, you cannot say anything about the other states, I guess. All right.
Thank you.
Yeah.
Any other questions? If no, like just I have a question actually, like just along the same line, like what Ada just asked. Like right now you are using the vertex state, so basically just taking the outgoing arcs over one. But like you can also like take like arcs around like one face, right?
Yeah. So what you're doing then actually it's completely dual. If you would look at
Okay.
so all these embeddings have duals, and then you do the dual thing. And actually the transition matrix for this dual walk is just the transpose of the original matrix, because you kind of replace both the reflections and you get the transpose.
Okay.
So yeah, you can do that too. Yeah.
Okay. Thank you.
Yeah.
So if there's no more question, let's send Vincent.
I had a question. Sorry. Yeah. So you just showed that you have periodicity and perfect state transfers on these toroidal grids. I was wondering, I guess it's hard in general to find perfect state transfer, but do you know any other examples of these graphs on tori or other orientable surfaces?
So I think we actually only had these, except maybe other like trivial examples where it's like only let me think. Like maybe variants on this trivial example that I showed before. We have like vertices going between left and right, but now it's like the ordering of the arcs is different, so that you need kind of an embedding with more holes in it. So that's like this is also in our paper. So we call this like, I think, dipoles or something, where it's like for every genus, so every number of holes, we have some kind of trivial embedding that gives you an example of PST, but it's always at like time 1. So that's not very, very interesting maybe, but yeah. And otherwise we didn't really find anything else. So maybe, yeah. But it turns out this requirement for PST, or we're trying to write down like a characterization for it now, and it's very specific. You need to have like specific these Chebyshev polynomials. If you plug in the eigenvalues, you need to get 1 or -1, and then it's like, yeah, you don't see this often, I guess.
I see. Thanks.
Okay. Yeah.